Okay, I'm recording another video for 114. So last time we learned the magnetic field energy, right? We discussed inductors, inductance. So these things are new, but everything has a definition, right? So you will see a lot of new definition in this part, but the questions are in this part are usually plug and chug, okay? The plugins, okay? So magnetic field energy, we also derived an equation for that, right? Which is this. The big U, we use the big U for the energy, from 1/2 Li squared, okay? And then we derived an equation for the magnetic field energy density, which is the UL. So the little u, okay? So don't be confused, this little u is the magnetic field density, okay? So that's the definition is this guy, the energy divided by the volume. And then we do have this is the definition, right? And we did we didn't derive that. Well, we derived that using a solenoid. But this is actually a general conclusion for any magnetic field. Any magnetic field carries energy, so that's why EM waves can transport energy. We're going to discuss that later. So if you want to find magnetic field energy density, you only need the magnetic field. And of course, the mu naught is a constant. Okay? Now, let's just practice these two equations. The first thing I want you to do is this. A solenoid use the MRI machine, okay, with this number, okay, I believe we have seen that before, right? And then find the magnetic field energy stored in this solenoid after the current, okay? So that's the solenoid we used last time, right? We already calculated the L. We already calculated the L. And then all you need to do is just use that equation. Okay, and then use the L we calculated last time. Okay, we calculated last time, and then use this equation. Okay, so this part is mostly plugins. Okay, and then the current is 2.3 kiloamps, so you convert it to amps. All right, so at the end you will get this is gonna be again, pause the video, do it. Okay, this is an easy one. Right, because the L we calculated last time using the equation for the solenoid, right? For a solenoid, the L is this. A divided by L. Okay, once you have that, you find the I. No, you don't find the I, I'm sorry. You find the energy. The I is given, right? 2.3 kiloamps. Now the next part, find the magnetic field energy density in the solenoid after the current has reached 2.3 kiloamps. Okay. Well, then in this case, there are two ways you can do that, right? Either you just do total energy divided by volume. That's the definition of magnetic field energy density, right? Or you can use this equation. This is a general equation for any magnetic field. You just find the magnetic field in this solenoid, which is going to be mu naught big N divided by length and times I, right? Either way, okay? You can find the energy density, which should be joules per cubic meter, right? Say if I want to just use this definition, the energy density is just going to be this number, right? Divided by volume. The volume of a solenoid, it's just going to be the area inside the solenoid, right? It's just going to be the area times the length. So it's just going to be pi r squared. Yeah, right? So that's one way to do that, right? I just use the definition because I already have the total energy. Energy density is just energy divided by volume. Or if you like, you can use this, a general conclusion, find a B in this magnetic solenoid, and then just use the constant mu naught. Either way, you will get B. And this is our energy density, it's joules per cubic meter. Okay, so that's this. So I finished this part. Now I'm going to tell you the one application, an important application of this inductor in real life. So that's slide 8. This is still lecture 17, right? So that's in the ignition system of cars, okay? Because we know that in order to ignite the fuel, okay, usually the car, there's a spark plug, and then it needs to produce a spark, and the spark is going to ignite the fuel. Okay, how does that spark plug produce this spark? It uses a very high voltage, right? It uses very high voltage to. It's like a lightning. Think about lightning. Okay. Then how does it generate such a high voltage? It needs, you see that it needs a tens of thousands of volts in this spark plug to generate a spark. So what is the voltage of your car? What is the voltage from the battery of the car? That's only 12 volts. That's only 12 volts, right? So that 12 volts cannot produce a spark. Okay, so how does it produce a spark? So this is a mechanism. So what happens is that this battery circuit is connected to an inductor. Okay, and this is an inductor. It has a has a lot of turns. Has a lot of turns on it, right? It has a lot of turns on it. So that means the L inductance is going to be very large, right? And remember, when you calculate the inductance, induced EMF, the value is going to be this, right? So it's just going to be L changing I divided by changing time. If the L is very big, right? If the L is very big, and also when the switch, when the switch is closed, right? There's a switch connected to this 12-volt battery. When the switch is closed, there's a sudden increase of the current through this inductor. So you will have a changing current divided by changing time. That's also very quick. If that happens really quick, this number is also very large, right? Because the time is very short. Both of them are going to be very large. So that's why at that very short amount of time, E&M and EMF, which is just a voltage of tens of thousands of volts, can be induced. So this is an induced EMF in the inductor. So that can cause a spark, and that spark can ignite the fuel in the car. Because the 12 volts from the battery of the car can never cause a spark. Okay, so that's a very important application of this inductor. Right? Now we have finished inductors, okay, and then we're going to move on to AC circuits. Okay, as I said, first of all, how do we generate electricity in real life? We use E&M induction, right? And then the best way to generate electricity, if you want to induce a current in a loop, right, you have to change the flux. That's Faraday's law. That's a law. And then the best way to change the flux is to change the angle, right? We learned that a lot before. And then the best way to change the angle is just rotate a loop inside a magnetic field, right? So that we have seen that image before. So in this case, the AC, the current you generate, the EMF, the voltage generated in this process is always changing. The magnitude and direction are changing all the time, right? So the voltage and current you get from this source, this AC source, is going to be a sine function. So take a look at the image on the right. Okay, that's going to be the function for the voltage. So it depends on where you start counting. It can be a cosine and sine, right? Because sine and cosine, the wave shape is the same, right? So you can see if you study AC circuits in different books, some books use sine function, some books use cosine function. It doesn't matter. It doesn't really matter, okay? The physics is still the same, Okay, so in this class we're going to use cosine, but again, as I said, it totally depends on where you pick as the 0 time, right? If you shift this 90 degrees to the left, it becomes sine function. Okay, so we can just use cosine, and then the voltage source in this class, AC voltage source, is always going to be in this form, always. Okay, now the voltage is going to be a varying voltage, right? It doesn't stay constant. It's going to change all the time. It's going to be a maximum value times a cosine function, right? So maximum value is easy to understand, right? Take a look at the image. A cosine function always has a maximum value, right? So this is going to be the voltage. This is also the voltage you get from this wall outlet, from all these wall outlets. Okay. So it's always going to vary between these two values. The negative sign just means it changes direction. Okay. We don't have negative voltage or negative current, right? It just changes direction. We always use signs to distinguish the direction. Okay. So this guy is going to be the maximum you can get. For example, if this is 10 volts, this is a negative 10 volts. So that means this actual voltage you get from these wall outlets is always going to change from 10 volts to negative 10, 10 volts to negative 10. Right? Now the angle of this omega is called angular frequency. Okay, so this is is defined as 2 pi divided by period. Right, so you remember the definition of this angular velocity. This is the angular velocity we define in physics 1, right? It's also connected to frequency because if you remember the frequency is 1 over period, right? So this guy is also going to be equal to 2 pi f. So that's why it's also called angular frequency, because it's 2 pi radians times frequency. So this unit is going to be radians per second, right? So this is exactly the angular velocity we define in physics 1. Okay, so that means if this is in radians per second, this number you calculate is going to be in radians. If this number is in radians, when you do cosine, make sure you're going to put your calculator in radian mode. Okay, when you do algebra in this part. Okay, so this is the voltage. So AC circuit is a little bit different than DC circuit, so that's why we want to study them in detail. So now the first thing we're going to study is that what if you connect a resistor to an AC circuit, right? So take a look at the image on slide 10. This is a simplest circuit, like resistor circuit. You just replace the battery we have been using with the AC source, right? Like you connect a light bulb to these wall outlets. A resistor connected to an AC source. Now, how do I solve this circuit? Well, that's pretty much like a DC circuit, right? What you do is that you can still use Ohm's law to solve this circuit. This is the AC circuit. There's a resistor connected to this circuit. This is the simplest circuit, resistor circuit, right? And then if you apply Ohm's law, you will get this. So the current is also going to be changing, right? Because the voltage is changing. So you just do voltage divided by resistance. Nothing special, right? And then at the end you will get. So then you can just divide this whole function by this R. What do you get? You just get V max over R, and then still times this cosine function. So the current you get is also going to be a cosine function, right? And then sometimes we usually just call this guy I max, right? Because this is going to be, you see, this is a cosine function. This function is going to vary from negative 1 to 1. So whatever this value is, the current is going to vary between positive and negative that value, right? So say if this current is going to be negative 2 amps to 2 amps. So 2 amps is going to be 2 amps is going to be the maximum current. So that's why we write it in a different form. We're going to call this thing I max. And then this looks nicer than that, right? That's the only reason, right? So then I would write this I max is going to be equal to V max over R. Okay, I just defined this so I can write it the same form as this voltage. So actually there's nothing special when you connect a resistor to AC source, right? You still do Ohm's law, and then the only difference is that the voltage and the current, they're both changing, but they're both a cosine function, and they both change the same way. So if you look at the image at the bottom, the voltage and the current, they always reach the top at the same, they always reach the zero at the same, they always reach the top in the opposite direction the same. So we say they are in phase. Their behavior is exactly the same, right? That's because you see, take a look at the function, right? They're exactly the same function, a number times cosine, a number times cosine, right? So of course they're going to behave the same. The only difference is that this number is going to be different, okay? So there's nothing special. If a resistor is connected to a AC source, okay, you still just do Ohm's law, do whatever we did before. It's just the voltage and current they're changing, right? And the reason we call them in phase is that we're going to see that when you connect a capacitor or inductor to an AC source, they don't behave the same way. They don't reach the maximum at the same point. They don't reach zero at the same point. So we call them out of phase. Okay, that's what we're going to see after resistance. Now let's take a look at, let's practice this. Let's take a look at the question on slide 11. So two resistors, okay, now it's still a resistor circuit, but now you have two resistors connected to it. These two resistors, they're connected in series or parallel? Series, right? They're connected one after the other. There's only one path in this circuit, right? There's nothing between them. The path doesn't split. That is a series circuit. Now I want to solve this series circuit. So let's see, let me draw it out. So you're just gonna still use the theories we learned for a series circuit to solve this, right? The only difference is that the voltage is gonna be a function. But let's see what we want to find. The voltage is 10 volts cosine 120 pi t, so that's the voltage. So that means it's changing, right? It's an AC source. You give me a time, I can calculate the voltage for you, but the voltage is pretty much like this. It's changing between 10 and negative 10, 10, negative 10 all the time. We want to find the instantaneous power of this 15 ohm resistor at t equals 30 milliseconds. Of course, if you want me to find the power, you need to give me a time because everything's changing. Voltage is changing, current is changing. What is the power of a resistor? The power is I times V. If I and V, they're both changing, of course the power is going to be changing. So if you want me to find the power of a resistor in an AC circuit, I would ask you, what is the time you want to find that, right? Because it's also going to be a function of time. So the problem says, find the power of this guy at t equals 30 milliseconds. Milliseconds, so that means all I need to do is that find the voltage at that time. Then just use the voltage to do this circuit analysis, right? The rest is going to be the same. So what is the voltage at that time? You're going to plug the 3 milliseconds in, right? So this is function. What is the voltage at that time? Plug the time in 30 milliseconds, 30, not 3. Right? So I'm just going to do 10 volts times cosine 120 pi. Convert this to seconds, 0.03. All right? Multiply this to 2, but again, make sure you put your calculator in radian mode because everything is going to be radians here. Okay? All the angles inside the cosine function. Okay? Use your calculator, find this voltage. And this voltage I found is 3.09 volts. Okay? Now I can just replace this with a DC circuit, right? Because I'm only interested in what happens at 30 milliseconds. So at 30 milliseconds, the voltage is 3.09 volts. So it's pretty much like these two resistors are connected to a 3.9 volt battery. Find the power of this 15 ohm resistor. Okay, and that's something we already know how to do that, right? How do I find the power of each of them for each of them? You just use the power equation, right? Because power equals I times V. So all I need to do, if I want to find power on this guy, I will just find the current through this guy, voltage through this guy. And I only need to find one, right? If you find a current, you can use Ohm's law to find the voltage. Or if you have the voltage, use Ohm's law to find current. So now let's see. Then the easiest way is to find the current, right? Because if this is a series circuit, we know that the total current, there's only one current here. Right? And then you can replace this with the equivalent circuit. And then the current is the same, right? Because they are in series. So, and then this equivalent resistance is just going to be the sum between them. That's the theory we learned for series circuit. All right, so the I total in this question is going to be this divided by Req. That's still Ohm's law, right? This number I found is about 15 amps. And then they're in series, so each of them is just going to get 0.15 amps, right? So if I want to find the power, this guy is going to get 0.15 amps. This guy is going to get 0.15 amps. How do you find the power of the second one? If I call this R2, this is R1, it's R2. Then P2, it's going to be I2 times V2. I2 is going to be equal, right? So I1 and I2, they will be equal to I2 because there's only one current in this series circuit. And then, but I don't have the voltage. But the voltage, if you have the current through R2, you can just use the Ohm's law to find the voltage, right? At the end, you see that you have all these numbers, right? You put all the numbers in, you will find the power. Okay? So there's nothing special if you connect a resistor to, or even like many resistors to an AC circuit, right? Well, you just find that if you want to find some instantaneous value, the problem is always going to tell you a time. So you just find a voltage at that time, and then replace the source with the voltage, with the battery with that voltage, and then just solve the circuit, the DC circuit, right? Nothing special, okay? So I don't even need to remember any theory for resistors connected to an AC source, right? It's pretty much like what we do in DC circuit. Right. Then, because you see that when I calculate the power, if you want me to calculate the power of a resistor in the AC circuit, I will always ask you about the time because the power is going to change, right? Because at the end I would do current times voltage, but these two numbers they're changing because this number is changing, so everything is changing in this circuit. Then you would say that okay. Then how come when I buy a light bulb, the light bulb has a rated power like 40 watts? Because I'm going to connect it to an AC outlet, right? So the power actually is going to be changing. Then how come there's a rated power? Well, the rated power is actually the average power of this light bulb. Because the power is changing, right? But we can still calculate an average power, right? If you want to calculate average power, what do you do with this, right? You just take a period of time, you do energy, total energy divided by time, you will get the average power, right? Say if you're running, even if you don't run at a constant speed, I can still calculate your average speed, right? I just use the total distance you run divided by the time you run. That's the average speed, right? I can still have an idea how fast you're running, right? So even though the power in the resistor connected to an AC source is changing, but I can still calculate the average power to see how fast it's using energy. So in this case, I can still do the total. I just pick a period of time and then find the total energy divided by time. And then the easiest time you can use is I'm just going to use a period, right? So if you use a period, which is t, then you're just going to calculate the power in one period. And then that can be derived. So in this case, you can't just multiply anything. If you want to find the energy in one period, you have to integrate the power by the time, right? So you're going to do the algebra. Now that's calculus. But at the end, you will get this. Then the top guy is going to become 1/2 I max V max times T. Okay, after you have done the math, okay, this is not intuitive at all, right? Because this is calculus, okay. And then you see that if I do this, then I will just get 1/2 I max V max. Okay, so that's a general conclusion. If a resistor is connected to a power AC source, I can still use these two maximum values to calculate the power. But I would just do 1/2 this I max times V max, which is a little bit different than the equation we have been using in a DC circuit. We just do I times V, because in a DC circuit, I and V, they don't change, right? So I don't need any subscript there. But in this case, V and I, they're changing. Only this V max and I max, they're constant, right? So I can only calculate average power using these two numbers. But I don't like that, because I don't like to have two power equations, which one is I times V, the other one is 1/2 I times V, whatever you call them, I max or V max. So what we do is this, we're gonna define something called RMS values, okay? So that's what we define in slide 12. So if I do this, I define an RMS value. This is just totally definition as V max over square root of 2. And I'm also going to define RMS value, V squared over I squared, I max over square root of 2. And then multiply these two numbers, you get what? You just get, because this is going to be I max times V max, you will just get square root times square root at the bottom, you get a 2. So if you multiply them together, you just get this average power we just derived. Right? If you multiply these two RMS values, you just get this. And then that's nicer, right? Because this agrees with the power equation in a DC circuit. And I like this, right? So if you want me to calculate the power in a DC circuit, or if you want me to calculate the power in the AC, the average power in an AC circuit, I always do I times V. I don't need to make a distinction, okay? In this case, I do I times V. In that case, I'm going to do 1/2 I max times V max, right? I'm just going to do I times V, but in this AC circuit, I just remember that I need to use RMS value instead of these maximum values, right? Okay, so that's the RMS values. Okay, and then when we talk about the voltage, okay, from this wall outlet, okay, anyone knows the voltage you get from this wall outlet in this country? That's 120. But this 120 is the RMS value, okay, because the actual voltage you get from this wall outlet, they're changing, right? Because that's a function. Cosine function is changing all the time, right? So if you tell me the voltage you get from this wall outlets is 120, what does that mean? It's the RMS value, okay? If that's the RMS value, 120, then what is the actual maximum value of this voltage you get from this wall outlets? You can use this equation to find them Vmax, right? So if the RMS value is 120, you rearrange this equation, the Vmax is going to be 170, right? So actually the voltage you get from all these wall outlets in this country, they will vary they will be like this, right? They will vary between negative 170 to 170, right? But we still say that the voltage we get from this wall outlet is 120 because we mean the RMS value. RMS value is Vmax divided by square root of 2, right? Okay? And then the period, so that means the current also you get from this wall outlet is also changing, right? But very rapidly, okay? You see that the period in this country for this AC current and voltage is 0.0167 seconds. The frequency is 60 hertz. So that means, for example, the lights in the room, right? The current is changing all the time, but it changes really fast. It's changing direction 60 times in a second. So it's going to oscillate like 60 times in 1 second. That's too fast for our eyes. That's why we don't really see that they're changing. We see it's like constant brightness, but actually it is changing. Okay, so that's the RMS value. Okay, when we talk about the voltage from any wall outlet, actually we're talking about the RMS value. The average power, right? When you say the power of a light bulb, we are talking about the average power. Okay. These are the difference between the RMS value and the maximum value. Now, and then if you go to a different country, that country may use a different voltage, right? For example, if you go to China, China uses 220 AC voltage, okay? So that means the RMS value of the voltage you get from a wall outlet in China is 220, okay? It's not 120. So then I want you to solve this problem for me, slide 14. If I tell you China uses 220 volt AC electricity, what is the maximum voltage you can get from a wall outlet in China? Okay, so again, it's the relation between RMS value and the maximum, right? When we say the voltage from a wall outlet is some value, we are saying the RMS value, okay? So we don't say like explicitly, but that's what we mean. So when I tell you China uses 220 AC voltage, I'm telling you the VRMS in China is 220. Then what would be the maximum voltage you can get from the wall outlet? You just rearrange this equation, right? You can find the maximum voltage you can get in China. That's going to be 311 volts. Okay, don't get them backwards. So that means if you go to China, the voltage you get from the wall outlets is going to be like this. It's going to vary from negative 311 to 311, right? Still oscillating, okay? But the RMS value is 220. So that's why that's what we say. That China uses 220 volt AC electricity, okay? But that's the RMS value. Now we have finished this lecture. Let's move on to the next one. Okay, so that's when you connect a resistor to an AC circuit. Nothing fancy, nothing special. You still use the theories we learned in DC circuit and just solve this circuit. The only new thing we learn is this: we define RMS value, RMS value. So if I calculate the average power of a resistor in an AC circuit, I can just go ahead and multiply I and V, but I just use RMS values. Okay. Now, but inductors, remember, we also learned capacitors and inductors. Okay, they are less familiar to most people, but they're still very important elements in circuits. So what if you connect the inductors or capacitors to an AC circuit? What's going to happen? So they are actually more interesting in AC circuits, okay, than resistors, because there's nothing special for a resistor. But if you connect the inductors and capacitors to an AC source, they behave really interesting. Okay, so let's see. Now, if I connect, let's first study inductor. An inductor connected to an AC source. So I'm going to draw it out. This is the AC source. An inductor is this, right? Like the symbol is like a solenoid. This is an inductor. I'm going to use L. Remember the symbol we use for inductor is L. Now the voltage is still this, right? The voltage is still a cosine function. But then in this case, what about the current? What about the current? Okay, what is the current? What is the form for the current? For an inductor, you can't use the Ohm's law, right? Ohm's law is only for resistance, right? You do V over R. But in this case, you can't do that, right? But you can still use Kirchhoff's rule, right? You can always use Kirchhoff's rules for any circuit, right? They are more powerful than Ohm's laws. If you apply Kirchhoff's rules in this circuit, you can't apply junction rule because there's no junction, right? And you can just apply loop rule, and there's only one loop. So you're just going to apply the loop rule once, delta V from the source, and then I'm going to call this delta VL. You add them together, you should get a 0. Okay? And then let's use the expression. So this V, I'm just going to write down the function, because I want to find, don't forget what we're doing. We are finding an expression for I. We're finding an expression for I, the current. Okay, we want to find the expression. Now this guy is an inductor, right? Inductor, we learned that the induced EMF, induced voltage on the inductor is negative L di over dt. Now we're going to use di over dt. Okay, all right? So that's what we're doing in the inductor. The induced EMF is going to be negative L di dt, or negative L changing I divided by changing time, right? Now this is going to be equal to 0. You can solve this equation. This is a differential equation. All you need to do is just put all the t's together, put all the d's, i's together, right? So at the end, you will solve this equation. First of all, you just move this term to the right. You get L di over dt. You should have learned how to solve this equation in the calculus class, right? And then you just divide both sides by L and multiply both sides by dt, right? And what do you get? You get di on the right hand side, and on the left hand side you just get V max over L cosine omega t and then dt. And you just integrate both sides, you can get a function for I, right? Okay, so I'm not going to go into detail. At the end, you will get an expression for I. So I'm going to erase this, I'm going to list it here. It's also a function, but this function, this is a solution to this differential equation, right? And this is going to be V max over, this is a solution, omega L cosine omega t, sine omega t. Because if you integrate cosine, you will get sine, right? Now we're going to use a identity, because I still want to write this current in cosine function, so I can compare it with this voltage function. So if you use that identity, okay, if you forget that, that's fine. So sine any angle is going to be equal to cosine that angle minus 90 degrees, which is 1/2 pi radians, right? So I'm going to just go ahead and use this equation, right? But they are equivalent. So I'm going to erase this form. I want to make sure I is also a cosine function. Okay, I'm going to erase this. Right? So we're not really interested in the duration. I'm not going to ask you to derive that. Okay, we're just going to use the conclusion. Now you see that, okay, this is also a cosine function. This is a cosine function. And then, but if you plot that, you actually get, so take a look at the graph on the right, bottom right. The current and the voltage, now they're out of the phase. They don't reach the peak at the same time. They don't reach the zero at the same time. right? Actually, the current is always behind the voltage by 90 degrees, right? So take a look at the 0. The voltage is going to reach maximum at 0, t equals 0, time equals 0, right? That's the beginning. But the current, you see that the current equals 0 at time equals 0. And the current is going to reach maximum a little bit later than this voltage, right? See that the green line is the voltage, the purple line is the current. The current reaches the peak 90 degrees after the voltage has reached the peak. So we say that the current is always behind the voltage by 90 degrees because there's a function, in this cosine function, there's a negative 90 degrees or 1/2 radius. Okay? So they are out of the phase, right? They're not the same as resistor. They are out of phase. Okay? And in this case, you see that if you take a look at this number, this is still going to be the maximum number this current can get, right? If this is 5, and this is a cosine function, so this guy is going to vary between -5 to 5. Right? So again, we're going to call this guy, we're going to define this guy as I max. And then I can write this current in a nicer form, a maximum value times cosine function. And Imax equals this, with Imax defined as this, okay? And then I can even define a thing like this. And then if you compare this equation with the Imax equation we get for a resistor, right? The Imax for a resistor, Imax is Vmax over R. So this omega L, whatever this is, behaves like a resistance, right? Because you see that this I, this V, this still looks like Ohm's law. I equals V divided by R. But this R is like omega L. So this is like the equivalent resistance of an inductor in an AC circuit. Okay, very interesting. So we're going to call this guy reactance. Okay, we just define it, right? So I'm going to call this guy reactance. I'm going to use the symbol XL for it. So I'm going to call this omega L. So this XL you can think of as just the equivalent resistance of this inductor in an AC circuit. Because at the end, then you can write I max equals V max over XL. So this XL is pretty much like the R in the resistor circuit, right? And that's the reason we define that, right? So by defining this thing, an inductor behaves like a resistor in an AC circuit, right? Because it still has Imax times cosine function. The only difference is that it's going to shift this current, okay, 90 degrees behind the current, and also the equivalent resistance depends on the inductance and the source, because the omega is the frequency, angular frequency of the source. If you connect it to a different source, actually the XL is going to change. So an inductor is very interesting. It's similar to a resistor, but it depends on the angular frequency, and then it's always going to change the phase of the current. It makes the current always 90 degrees behind the voltage. Okay? I'm going to stop here.